Okay, this is the review lecture for the first part of the course, the AX equal B part of the course, and the exam will emphasize Chapter 3, because those are Chapter 3 was about the rectangular matrices where we had null spaces and null spaces of A transpose and ranks and all the things that are so clear when the matrix is square and invertible. They became things to think about for rectangular matrices. So, and vector spaces and subspaces, and above all, those four subspaces. Okay, I'm thinking, to start at least, I'll just look at old exams, read out questions, write on the board what I need to, and we can see what the answers are. The first one I see is one I can just read out. Well, I'll write a little. Suppose U, V, and W are non-zero vectors in R7. What are the possible? They span a vector space. They span a subspace of R7, and what are the possible dimensions? So it's a straightforward question. What are the possible dimensions of the subspace spanned by U, V, and W? Okay, 1, 2, or 3. Right. 1, 2, or 3. Couldn't be more because we've only got 3 vectors. And couldn't be 0 because I told you the vectors were non-zero. Otherwise, if I allowed the possibility that those were all the 0 vector, then the 0-dimensional subspace would have been in there. Okay. Now, can I jump to a more serious question? Okay. We have a 5 by 3 matrix, and I'm calling it U. I'm saying it's in echelon form, and it has 3 pivots, R equal 3. 3 pivots. Okay, first question, what's the null space? What's the null space of this matrix U? So this matrix is 5 by 3, and I find it helpful to just see visually what 5 by 3 means, what that shape is. 3 columns in U, then 5 rows, 3 pivots, and what's the null space? The null space of U is, and it asks for of course I'm looking for an answer that isn't just the definition of the null space, but is the null space of this matrix with this information. And what is it? It's only the 0 vector, because we're told that the rank is 3, so those 3 columns must be independent. No combination of those columns is the 0 vector, except, so the only thing in this null space is the 0 vector. And I could even say what that vector is, 0, 0, 0. That's okay. So that's what's in the null space. All right, let me go on with, this question has multiple parts. What's the, now it asks you about a 10 by 3 matrix, B, which is the matrix U and 2U. Actually, I would probably be writing R and maybe I should be writing R here now. This exam goes back a few years when I emphasized U more than R. Now, what's the echelon form for that matrix? So the echelon form, what's the rank and what's the echelon form? Let's suppose this is in reduced echelon form so that I could be using the letter R. So I'll ask for the reduced row echelon form. So imagine that these are, U is in reduced row echelon form, but now I've doubled the height of the matrix. What will happen when we do row reduction? What row reduction will take us to what matrix here? So you start doing elimination. You're doing elimination on single rows, but of course we're allowed to think of blocks. So what's the answer look like? U and 0, or R, I'll stay with this letter U, but I'm really thinking it's in reduced form, and 0. Okay, fine. Then it asks, further it asks about this matrix. U, 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 and 0. Okay, what's the echelon form of this? So it's just like practice and thinking through what would row elimination, what would row reduction do? Have I thought this through? So what are we, if we start doing elimination, basically we're going to subtract these rows from these. So it's going to take us to U, U, 0, and minus U, I guess, right? Take the thing all the way to R. Let's suppose U is really R. Suppose that we're really going for the reduced row echelon form. Then would we stop there? No. We would clean out, we could use this to, is that right? So I took these rows away from these to get there. Now I take these rows away from these, so that gives me 0. There. And now what more would I do if I'm really shooting for R, the reduced row echelon form? Then I want plus 1s in the pivot, so I would multiply through by minus 1 to get plus there. So essentially I'm seeing reduced row echelon form there, and there's just one little twist still to go. Do you see what that final twist might be? To have, if U is in reduced row echelon form, and now I'm looking at U, there's one little step to take. This isn't like a big deal at all, but if I really want this to be in reduced form, what would I still, might I still have to do? I might have some 0 rows here. I might have some 0 rows here that strictly should move to the bottom. Well, I'm not going to make a project out of that. Okay. What's the rank of that matrix? What's the rank of this matrix C? Given that I know that the original U has rank 3, what's the rank of this guy? 6, right. That has rank 6, I can tell. What's the rank of this B while we're at it? The rank of B, is that 6 or 3? 3 is right. 3 is right, because we actually got it to where we could just see 3 pivots. Okay. Now finally, this easy one. What's the dimension of the null space of C transpose? Oh boy. Okay, so what do if I want the dimension of a null space, I want to know the size of the matrix. So what's the size of the matrix C? It looks like it's 10 by 6, is it? 10 by 6, so C is 10 by 6. So M is 10. So C has 10 rows. C transpose has 10 columns, so there are 10 columns there. So how many free variables have I got? Once I start with the 10 columns in C transpose, that's the M for the original C. And what do I subtract off? 6, because we said that was the rank. So I'm left with 4. Thanks. Okay. So I think that's the right answer. The dimension of the null space of C transpose would be 4. Right. Okay. Yeah. Okay. So that's one question. At least it brought in some of the dimension counts. Okay. Here's another type of question. I give you an equation, AX equals 2, 4, 2. And I give you the complete solution. But I don't give you the matrix. And there's another vector 0, 0, 1. Okay? All right, my first question is, what's the dimension of the row space of the matrix A? So the main thing that you want to get from this question is that a question could start this way, sort of backward way, by giving you the answer and not telling you what the problem is. But we can get a lot of information, and sometimes we can get complete information about that matrix A. Okay. So what's the dimension of the row space of A? What's the rank? Tell me about what's the size of the matrix. Yeah, these are the things we want to think about. What's the shape of the matrix, first of all? It certainly has 3 rows. But is it 3 by 3? Do the x's that it multiplies have 3 components? So that does the matrix have 3 columns also? Yes. So I'm seeing the same length in B, 3, and also in X. So A is a 3 by 3 matrix. And what's its rank? Its rank? Tell me something about its null space. I heard the right answer for the rank. The rank is 1 in this case. Why? Because the dimension of the null space, so the dimension of the null space of A is, from knowing that that's the complete solution, it's 2. I'm seeing 2 vectors here, and they're independent in the null space of A because they have to be in the null space of A. If I'm allowed to throw in to the solution any amount of those vectors, that tells me that's the null space part then. So the dimension of the null space is 2, and then of course I know the dimensions of all 4 subspaces. Now actually it asks, what's the matrix? What's the matrix in this case? Shall I try to figure that out? Sure. You'd like me to do it? Okay. So what about the matrix? Or let me at least start it. Okay. If A times this X gives 2, 4, 2, what does that tell me about the matrix A? If A times that X solves that equation, then that tells me that the first column of A is 1, 2, 1. Right. The first column of A has to be 1, 2, 1 because if I multiply by X, that's going to multiply just the first column and give me 2, 4, 2. And then I've got 2 more columns to find. And what information have I got to find them with? I've got the null space. So the fact that this is in the null space, what does that tell me about the matrix? A matrix that has 0, 0, 1 in its null space? That tells me that the last column of the matrix is zeros. Because this is in the null space, the last column has to be 0. And because this is in the null space, what's the second column? Well, this in the null space means that if I multiply A by that vector, I must be getting 0, so I think that better be -1, -2, and -1. Okay, that's a type of question that just brings out the information that's in that complete solution. Okay. And then I go on to ask, for what vectors B can AX equal B be solved? AX equal B can be solved if, so I'm looking for a condition on B, if any. Can it be solved for every right-hand side B? No, definitely not. When could it be solved? Well, I actually say in the exam, don't just tell me if B is in the, and what does the exam say there? In the column space, because I do know that it can be solved exactly when B is in the column space. So I guess I'm asking you, what is the column space for this matrix? So what is, if B has the form, so I guess I'm asking you, what's the column space of this matrix? And what is it? It's, so the column space of that matrix is all multiples. B is a multiple of 1, 2, 1, right? I can solve the thing if it's a multiple of 1, 2, 1, and of course, sure enough, that was a multiple of 1, 2, 1, and so I had a solution. So this is a case where we've got lots of null space. Let me just recall that the other extreme, when the rank is big, don't forget those cases. Don't forget the other cases when R is as big as it can be, R equal M or R equal N. Those we had a full lecture on that, full rank, full lecture, and important case. Okay. I'll just move on. I think this is the best type of review. It just brings these ideas out. Apologies to the camera while I recover glasses and exam. Okay. How about a few true-false ones? Actually, there won't be a true-false on the quiz, but it gives us a moment of quick review. Here's one. If the null space, I have a square matrix. If its null space is just the 0 vector, what about the null space of A transpose? If the null space of A is just the 0 vector and the matrix is square, what do I know about the null space of A transpose? Also the 0 vector. Good. And that's a very, very important fact. Okay. How about this? Look at the space of 5 by 5 matrices as a vector space. So it's actually a 25-dimensional vector space, all 5 by 5 matrices. Look at the invertible matrices. Do they form a subspace? So I have this space of all 5 by 5 matrices. I can add them, I can multiply by numbers, but now I narrow down to the invertible ones, and I ask, are they a subspace? And your answer is? Quiet, but nevertheless definite? No, right? No. But if I add two invertible matrices, I have no idea if the answer is invertible. If I multiply that invertible, well, it doesn't even have the zero matrix in it. It couldn't be a subspace. I have to be able to multiply by zero and stay in my subspace, and the invertible ones wouldn't work. Well, the singular ones wouldn't work either. They have zero. The zero matrix is in the singular matrices, but if I add two singular matrices, I don't know if the answer is singular or not. Okay. So, another true-false. If b, here we go, here's it. If b squared equals 0, then b equals 0. True or false? If b squared equals 0, true, false. B squared equals 0, b has to be a square matrix so that I can multiply by itself. Does that imply that b is 0? Are there matrices whose square could be the zero matrix? Yes or no? Yes, there are. There are matrices whose square is the zero matrix. So this statement is false. If b squared is 0, we don't know that b is 0. For example, the best example is that matrix. That matrix is a dangerous matrix. It will come up in later parts of this course as an example of what can go wrong. And here's a real simple, so if I square that matrix, I do get the zero matrix. And it shows, of course. Yeah. Okay. All right. Here, a system of, a system of n equations in n unknowns is solvable for every right-hand side if the columns are independent. Okay. So can I say that again? It's n, I'll write it down then for short. N by n matrix, independent columns. Then the question is, does AX equal B? Is it always solvable? And the answer is yes or no. Right. Okay. Let's have. Did you watch that quiz? There was a quiz program on TV for a few weeks. Did you see that? What was the name of that? Winning $1 million or something? How to be a millionaire? With some crazy guy. What was his name as the MC? Regis. Right, Regis. Okay. If you saw this, like when you should have been doing linear algebra, of course. But I didn't have to do the homework, so I was watching it. So there were three. The novel point was there were three ways that you could get help, right? But you could only use each way once, so you couldn't use them all the time. So you remember that? You could poll the audience, and that was a 100% successful way. So I'll poll the audience on this. Another possibility, you could call your friend, right? Or he's your friend until he gives you the wrong answer. Which that turned out to be very unreliable. You know, you call up your brother or something and ask him for the capital of whatever, Bosnia, and what does he know? He makes some guess, and it costs you $500,000. So, but polling the audience always works. So let me say yes. Yes or no. If I have square matrix, independent columns, is AX equal B always solvable? Maybe just hands up for that. A few. And who says no? Oh gosh, this audience is not reliable. It's 50-50. I guess I'd vote yes, because independent columns, that means that the rank is the full size n. I have a matrix of rank n. That That means it's square, so it's an invertible matrix, and nothing could go wrong. Yeah. So that's the good case that we always expected in chapter 2, but of course chapter 3 that's only one of the possibilities. Okay, let me move on to another question from an old quiz. Okay. Let's see. Okay, I'm going to give you a matrix, but I'm going to give it to you as a product of a couple of matrices. 1, 1, 0, 0, 1, 0, 1, 0, 1, times another matrix, 1, 0, minus 1, 2, 0, 1, 1, minus 1, and all zeros. Okay. I would like to ask you questions about that matrix without doing the multiplication and finding the matrix B. Can you tell me something? So I'll ask questions about this matrix B, and I'll answer them without multiplying it out. For example, I'm going to ask you for a basis for the null space. A basis for the null space. So I'm going to solve Bx equals 0. So give me a basis for the null space of B. Let's see, what dimension am I in? The null space of B is the subspace of R. What size vectors am I looking for here? Because if we don't know the size, we aren't going to find it, right? This matrix is 3 by 4, obviously. So if we're looking for the null space, we're looking for those vectors x in R4. Okay, so the null space of B is certainly a subspace of R4. What do you think its dimension is? Of course, once we find a basis, we would know the dimension immediately, but let's stop first. What's the rank of this matrix B? Let's see. Is that matrix invertible, that square one there? Let's say sure. I think it is. Yeah. That matrix B looks invertible. Is that pretty clear? Yeah. So I've gone wrong in this course already, but I'll still hope that matrix is invertible. Yeah. Because if I look for a combination of those 3 columns, well, I couldn't use this middle column because it would have a 1 in a position that only is otherwise all 0. So a combination that gives 0 can't use that column, and then the other 2 are clearly independent steps. So that matrix is invertible. Later we could take its determinant or other things. Okay, what's the setup? If I have an invertible matrix, a nice invertible square matrix times this guy, times this second factor, and I'm looking for the null space, does this have any effect? So what I'm asking is the null space of B the same as the null space of just this part? I think so. If Bx is 0, then multiplying by that guy, I'll still have 0. But also, if this times some x gives 0, I could always multiply on the left by the inverse of that, because it is invertible. And I would discover that this times the x is 0. You want me to write some of that down? If I have a product here, C times D, say, and if C is invertible, the null space of CD will be the same as the null space of D if C is invertible. Multiplying by an invertible matrix on the left can't change the null space. Okay, so basically I'm asking you for the null space of this one. I don't have to do the multiplication because C is invertible. That first factor C is invertible. It's not going to change the null space. Okay, so can we just write down a basis now for the null space? So what's the basis for the null space of that? So basis for the null space, I'm looking for the two. There are two pivot columns, obviously. It clearly has rank 2. I'm looking for the two special solutions. They'll come from the third and the fourth. The free variables. Okay, so if the third free variable is a 1, then I think probably I need a -1 there and a 1 there, it looks like. Do you agree that if I then do that multiplication, I'll get 0? And if I have 1 in the fourth variable, then maybe I need a 1 in the second variable and maybe a -2 in the third. So I just reasoned that through, and then if I look back, I see, sure enough, that the free variable part that I sometimes call F, that 2 by 2 corner, is sitting here with all its signs reversed. So here I'm seeing -F, and here I'm seeing the identity in the null space matrix. Okay, so that's the null space. Another question is, solve Bx equal 1, 0, 1. Okay, so that's one question. Now solve complete solution to Bx equals 1, 0, 1. Okay. Yeah, so I guess I'm seeing, if I wanted to get 1, 0, 1, what's a particular solution? So I'm looking for a particular solution and then the null space part. Okay, actually the first column of B, what's the first column of our matrix B? It's the vector 1, 0, 1. The first column of our matrix agrees with the right-hand side. So I guess I'm thinking X particular plus X null space will be the particular solution. Since the first column of B is exactly right, that's great. And then I have C times that first null space vector and B times the other null space vector. Right? The null space part of the solution, as always, has the arbitrary constants. The particular solution doesn't have any arbitrary constants. It's one particular solution, and in this case, that one would do it. Okay, fine. So those are questions taken from old quizzes. Any questions coming to mind? Yeah.
I don't understand how you got X particular.
This X particular guy. Okay. Well, so that particular X particular says that, see, when I multiply by this guy, I'm going to get the first column of B. If that's a solution, when I multiply B times this X will be the first column of B. And so I'm saying that the first column of this B agrees with the right-hand side. So I'm saying that look at the first column of that matrix B. If you do the multiplication, so what's the first column of that matrix? Is that how do you do that multiplication? I multiply that matrix by that first column, and it picks out 1, 0, 1. So the first column of B is exactly that. And therefore, a particular solution will be this guy. Yeah. Okay. Yes?
Is there only one particular solution?
Is there only one particular solution? No, not at all. No, I could, I mean, this is a nice one, but any solution could be the particular solution. Any of the solutions can be the particular one that we pick out. Like this plus this would be another particular solution. It would be, in other words, it would be another solution. The particular is just telling us only take one, but it's not telling us which one we have to take. We take the most convenient one. I guess in this problem that's that one. Good. Other questions? Yeah. And this pattern of particular plus null space, of course, that's going throughout mathematics of linear systems. We're really doing mathematics of linear systems here. Our systems are discrete and they're finite dimensional, and so it's linear algebra. But this particular plus null space goes, that doesn't depend on having finite matrices. That spreads everywhere. Okay, I'm going to just like to encourage you to take problems out of the book. Let me do the same myself. Okay, well, here's some easy true or falses. I don't know why the author put these in here. Okay. If m equals n, then the row space equals the column space. So these are true falses. If m equals n, so that means the matrix is squared, then the row space equals the column space. False. Good. Good. What is equal there? Well, what can I say is equal? If n, well, yeah. Yeah, so that's definitely false. The row space and the column space. And this matrix is like always a good example to consider. So there's a square matrix, but its row space is the multiples of 0, 1, and its column space is the multiples of 1, 0. Very different. The row space and column space are totally different for that matrix. Now, of course, if the matrix was symmetric, well, then clearly the row space equals the column. Okay. How about this question? The matrices A and minus A share the same four subspaces. Do the matrices A and minus A have the same column space? Do they have the same null space? Do they have some row space? What's the answer on that? Yes or no? Yes. Good. Okay. How about this? If A and B have the same four subspaces, then A is a multiple of B. Suppose those subspaces are the same, then is A a multiple of B? Okay, how do you answer a question like that? Of course, if you want to answer it yes, then you'd have to think of a reason why. If you want to answer no way, then you would, and I would sort of like, first I would try to think no. I would say, can I come up with an example where it isn't true? Let me repeat the question, and then write the answer. Okay, so I'll repeat that question. True or false? If A and B have the same four subspaces, then A is some multiple of B. True or false? How do you feel about it at this instant? Got quite a few true, so I take a poll. So how many think true? Okay. We gave you every chance to think about that. let's see. So what I would just take extreme cases if it was me. So when do I know? Well, I would say suppose a matrix is invertible. Suppose A is an invertible matrix. Then what? Suppose it's 6 by 6 invertible matrix. Then what's its row space? And its column space is all of R6. And the null space, then the null space of A transpose would be the 0 vector. So every invertible matrix is going to give that answer. If I have a 6 by 6 invertible matrix, I know what those subspaces are. Heck, that was back in chapter 2 when I didn't even know what subspaces were. The row space and column space are both all 6-dimensional space, the whole space, and the rank is 6, in other words, and the null spaces have 0 dimension. So you see now the answer? So A and B could be, for example, so I'm going to say false. Because A and B, for example, so an example, A and B, any invertible 6 by 6. 6 by 6. So those would have the same 4 subspaces, but they wouldn't be the same. Of course, there should be something about those matrices that would be the same. So it's sort of a natural problem. So now actually we're getting to a math question. The answer is, this is not true. One matrix doesn't have to be a multiple of the other. But there must be something that's true. And that would be sort of like a natural question to ask. If they have the same subspaces, same 4 subspaces, then what could you then say about those matrices? Yeah, maybe let me leave that as an open question. Just sort of because the instinct wasn't necessarily right. But I hope you now see that the correct answer is false. And then you might think, okay, well, they certainly do have the same rank. But obviously, if they have the same 4 subspaces, they have the same rank. I might say if they have this, well, yeah. Yeah, I could extend that question and think about other possibilities and finally come up with something that was true. But I won't press that one. Let me keep going with practice. And these practice questions are quite appropriate, I think, for the exam. Okay. Let's see. If I exchange 2 rows of A, which subspaces stay the same? So I'm trying to pick out questions that we can answer without, we can answer quickly. If I have a matrix A and I exchange 2 of its rows, which subspaces stay the same? The row space does stay the same, and the null space stays the same. Good. Good. Correct. Column space would be a wrong answer. Okay. Here's a question. This leads into the next chapter. Why can the vector 1, 2, 3 not be a row and also in the null space? Let me close with this question. Close this. So V, this 1, 2, 3 can't be in the null space of a matrix and the row space. And my question is, why not? Why not? So this is a question that we can, because it's sort of asked in a straightforward way, we can figure out an answer. Well, actually, yeah. I'll even pin it down. It can't be in the null space and be a row. I'll even pin it down further. Ask it to be a row of A. Why not? So we know the dimensions of these spaces. But now I'm asking you sort of like the overlap between. So the null space and the row space, those are in the same n-dimensional space. Those are both subspaces of n-dimensional space, and I'm basically saying they can't overlap. I can't have a vector like this, typical vector, that's in the null space and it's also a row of the matrix. Why is that? So that's a new sort of idea. Let's just see what it would mean. I mean that A times this V. Why can this A times this V? It can't be 0. Well, if it's 0, so I'm getting it into the null space here. So this is, now let's put that vector, now that vector is in the null space. Why can't the first row of the matrix be 1, 2, 3? I can fill out the matrix as I like. Why is that impossible? Well, you're seeing it's impossible, right? If that was a row of the matrix and in the null space, that number would not be 0, it would be 14. Right. So now we actually are beginning to get a more complete picture of these four subspaces. The two that are over in n-dimensional space, they actually only share the 0 vector. The intersection of the null space and the row space is only the 0 vector. And in fact, the null space is perpendicular to the row space. That'll be the first topic. Let's see, we have a holiday Monday, and I'll see you Wednesday with perpendiculars. And I'll see you Friday. So good luck on the quiz.